Welcome back. Today, as part of the discussion on the carbocation, we are going to see carbocation rearrangements. Today, we will be discussing two carbocation rearrangements. The first carbocation rearrangement we are going to discuss is the Wagner Meerwin rearrangement. We have already discussed an idea, a basic concept of the Wagner Meerwin rearrangement in the last class. You can see that here, Wagner Meerwin rearrangement is the carbocation rearrangement. You can see that here in this molecule, this is an alcohol, it's a secondary alcohol. You can see that here, when it is treated with an acid or acidulated water, the acidated water protonates the alcohol. And you can see that as a result of that, there will be H plus coming to this oxygen atom and it forms OH plus. It's actually a protonated alcohol. From this, water goes out, eliminates out. As a result of that, this secondary carbocation is formed. A secondary carbocation is formed. You know, when you compare secondary carbocation with tertiary carbocation is more stable. Therefore, here in this position, there is an alkyl group. Alkyl group is migrated towards this position. It is called 1,2-alkyl shift or 1,2-R shift. When it shifts from this place to this place, the valency, this carbon atom gets positive charge. It takes an electron and go. Methyl shift is actually happening. This carbon gets a positive charge. It is actually a tertiary carbocation. It's a tertiary carbocation. Now, what can happen is that the tertiary carbocation, in presence of water, this water will take this hydrogen atom, and you can see that here this O will abstract the proton and gives the bond to this position, and an alkene is formed. So acids and acid catalyzed reaction. For that means we have a acid related water here and it's given, we get it back. So it's an acid catalyzed reaction. So it's actually an example of an acid catalyzed reaction. So this migration of hydride ion or methyl ion or alkyl ion to get more stable carbocation is called Wagner Meerwin rearrangement. So it's actually an example. This R and R is actually methyl group here. The same reaction is mentioned over here. The same mechanism is actually explained. You can see this is the alkene that we obtain. So you can see that here the carbocation is migrated. Here we can see that who is migrating. In this example, this is actually what is happening here, and we get a compound like this. So the methyl ion, CH3 minus is migrating here. So the migrating group is CH3 minus ion is migrating. So methyl 1,2 shift. Okay, so this is actually the mechanism of Wagner Meerwin rearrangement. Now, a typical example of Wagner Meerwin rearrangement is as follows. This is actually isoborneol. It's isoborneol. We can convert isoborneol to camphene. Okay, so here again what happens is that here there's protonated water. As our protonation happens as it presents, there will be first protonation of this OH, and there will be here what happens later, the water is removed off and we get a carbocation. Here what happens is that there is a positive charge carbon atom here. The sigma bond migrates to this carbon atom, and as a result of that, a new bond is formed between this carbon atom and this carbon atom. A new bond is formed here, and this carbon atom gets a positive charge. You can see that a new bond is formed over here, and this bond is broken and it's like this. Okay, it forms like that. Okay, in other words, what can happen is that there can be, this is the system here, this is system here. This will be behaving like this. This is the CH3. These both are same. You can see this is the first carbon or second carbon. the first carbon containing the system and the second carbon containing the system. If you could analyze second carbon, and this is the third carbon, fourth carbon, fifth carbon, and sixth carbon. This is the first and second is explained here. First, second, and this is the third carbon, fourth carbon, fifth carbon. Okay, I can see this is the by sixth carbon is here. It's not sixth carbon here. The cyclic ring is over here. Okay, and we get a system like this. It's actually more the same. Okay, again, what happens is that here there is a possibility of what we say a methyl shift here. This is actually a tertiary carbocation. Here what happens is that the removal of proton is happening here, and as a result of that, this alkene is formed as a co-product, and this is camphene. So you can say here there is migration of this bond to this bond, and it's actually a secondary carbocation initially formed. Second is a secondary carbocation. This is converted to a tertiary carbocation. It's converted to tertiary carbocation. So here a secondary carbocation is converted to a tertiary carbocation, and you know what happens is that based on this there will be elimination happening here. You know the Bredesol, because of Bredesol, this elimination is not possible. This elimination is not possible because there is no free hydrogen atom. We have got only hydrogen atom in this carbon atom, and it will undergo the removal of H plus here, and a camphene is formed. Another example is this compound. It's a neopentyl bromide. This compound not treated with water in presence of acid is low. Actually, this compound is in fact formed. We expect the OH to be present in this position. We expect neopentyl alcohol, but we are not getting neopentyl alcohol here. The reason is that here it undergoes elimination and forms a primary carbocation. It's actually a primary carbocation. This primary carbocation is here because of the methyl shift. This CH3 will come here, and this carbon gets a positive charge. That is actually a tertiary carbocation. Here the primary carbocation becomes a tertiary carbocation, highly stable carbocation, and this on treatment with water will become a tertiary alcohol. So we expect a primary alcohol, but we are ending with a tertiary alcohol. So this is another example of what we say is the carbocation rearrangement or the Wagner Meerwin rearrangement. So these are the other examples. We can see that here. Here there is the compound. This is a microcyclic system, and there is H plus is adding here. H plus is adding here, and you know this here. When the H plus adds, there will be multiple migration of bonds taking place here, and it forms this compound. Okay, so we can see that here from this OH, this migrates over to this position. And this bond shift, needle shift over here. This needle will be coming to this side. See, this needle coming to this side. Okay, and this hydrogen undergo elimination, and this double bond is added towards H plus, and this product is formed. It is not a classical example, but we cannot observe arbitrary or clear needle shift or hydrogen shift here, but still it's a good example of Wagner Meerwin rearrangement. Now, let us see this example. This is starting compound. This compound is OH. You know that there is the presence of, after the reaction, there will be elimination with sulfuric acid, there will be a plus charge over here. Now what happens? This double bond migrates to this carbon atom, and as a result of that, an expanded product is formed. A 4-member ring becomes a 5-member ring. Later what happens is that this when this OH, again, when protonated, will become a system like this. There will be OH2 plus and methyl here. And you know, there will be elimination of water here. As a result of the elimination of water, we will be getting a positive charge here and 2 methyl shifts here. You can see that here it is a secondary carbocation. There will be 1,3-methyl shift. As a result of that, this CH3 is migrated towards this carbon atom. When it migrates, we will be getting a system like this because it's actually a tertiary carbocation. There's hydrogen here, this eliminates here, and it gives this product. Okay, this is another example of the reaction in which we'll be having Wagner Meerwin shift. So there are two Wagner Meerwin shift possible here. The tertiary carbocation is formed here. This tertiary carbocation, the sigma bond breaks and migrates to this carbon atom. So there will be expansion of the ring. This is a Demjanov reaction. Or this expansion of the ring here. It gives an alcohol. This on acidification. What happens is that there will be possibility of elimination and it forms this alkene as a result of the second Wagner Meerwin shift. Now let us take the case of alpha pinene. Alpha pinene, this is alpha pinene molecule. This compound on treatment with HCl, it forms Markovnikov addition and it forms this compound. This compound is formed. It's highly unstable, and what happens is that this become bornyl chloride. It undergo isomerization and form bornyl chloride. This compound will give camphene, and which again will give isobornyl chloride. Okay, so you can see this is not that much important as far as you are concerned, but I am just telling you that this Wagner Meerwin rearrangement is very vital in many skeletal rearrangements. Okay, so this is called Wagner Meerwin rearrangement. So I don't suggest you to study and understand mechanism of this process and this process, but the remaining systems you can easily understand. That's all about the Wagner Meerwin rearrangement. The next discussion is about the Pinacol-Pinacolone rearrangement. Pinacol-Pinacolone rearrangement is a classic rearrangement. This observed in 1860s by Fittig. So Pinacol, you might have studied this reaction during your degree classes. This is actually Pinacol. Pinacol is a diol. It's a vicinal diol where two OH groups are in the adjacent carbon atoms. It's a vicinal diol. One OH undergo protonation and it forms a carbocation. This OH undergo protonation forms a carbocation. What happens is that this carbocation undergo migration. This CH3 is coming over here. Okay, as a result of that, this carbocation is formed, and this carbocation gives its lone pair of electron to this plus charge, and it forms a ketone and forms Pinacol. This is actually what is called the Pinacol-Pinacolone rearrangement. Here, this carbocation is already stable. Then you may ask me why there is rearrangement. This rearrangement is in fact for this OH, for the stabilization of the oxonium ion. So it forms the Pinacolone here. Okay, so the driving force behind the reaction is found to be the relative stability of the resultant oxonium ion. Okay, so it is not the stability of the carbocation that concerns here, but the stability of the oxonium ion. And here the regioselective chemistry of the reaction is very important. Okay, so here we can see that migration. Here we can see methyl group is migrating. Okay, so if there's hydrogen atom, H hydride ion will be migrating. So if you look into the order of the migratory aptitude, it is found that alkyl group, tertiary alkyl group, migrates very fast. Then cyclohexyl, then secondary alkyl group, then benzyl group, phenyl group, primary alkyl group, methyl group, and hydryl group. So you can see that hydryl group will be having least affinity to migrate, but the tertiary alkyl groups are having the highest affinity to migrate. In the case of aromatic, I'm sorry about spelling here, aromatic. Okay, aromatic systems, we can see that if there is a electron donating substituent in the aromatic ring, like para-methoxy ring, the migratory aptitude increases. Here also, we can see that this para-methyl it is orthomethyl, orthomethoxy, chloro, bromo, etc. It will decreases. But para, it's actually para nitro aromatic. Para nitro withdrawal system, so it is having less magnetic aptitude. If the aromatic ring is having a methoxy system, it will be electron donating and it will migrate fast. We will understand more when we study more examples. It's a typical example again that is discussed over here. It's actually a bit more clear. You can see that here there will be a sulfuric acid. There's hydrogen transfer. As a result of that, there is a protonated pinacol. This pinacol undergo leaving group dissociation. There will be leaving groups giving water, is giving or give out. Now what happens? There is CH3 migrates to here. Neither shift is happening, rearrangement, and later there will be transfer of the bond shifted. The double bond is shifted towards here. You can see there is presence of oxonium ion here. Oxonium ion stability is very important. Later, the proton, this is deprotonated and give pinacol. Now, this is the example of a pinacol. It's an example of a pinacol. It's a very important example. It's actually pinacol. 1, 2. It's a vicinal diol pinacol. This compound on treatment with an acid in presence of BF3-ETO is a Lewis acid again. In presence of H+, what happens? It undergoes deprotonation and this carbocation is formed. This carbocation is formed. Now what happens is that this carbocation undergo a migration. This methyl group, this bond, sigma bond is migrated to the carbon atom. So there is a new bond to be formed between this carbon atom and this carbon atom. And this bond is going to break. It's actually a 6-membered ring. Now, actually what happens, this bond is converted to this system. Therefore, there will be 7-membered ring. It forms a 7-membered ring. It's actually 6-membered. It's actually 6-membered. 6-membered, 6-membered. It's actually 6-membered. It's actually all 6-membered. But here what happens, because of this breakage of bond and shifting towards this bond, there is actually a 7-membered ring. It's actually what is called the expansion of the ring. An expansion. Later, what happens? It forms a carbocation here to undergo elimination of proton, and it forms this compound. It's actually a pinacolone. Okay, this is actually an application of pinacol-pinacolone rearrangement. Please go through this example, and if you have doubts, you can contact me. Is it clear? If it's clear, we are going to see next topic, next example. Okay, so this is actually the orbital picture of the pinacol-pinacolone rearrangement. It's actually that we have discussed the basic things before. We can see that I have just written what this actually is given here. The driving force in pinacol-pinacolone rearrangement is formation of the oxonium ion. As I told you, we need a better stabilized oxonium ion. That's more important. So some of the selected pinacol-pinacolone rearrangements. You can see that here this is an example of a pinacol. We can try whether you can see this product. You can obtain this product. Okay. Again, try to explain the different products that you obtained here. Okay, this is considered to be your classwork. Here you can see it's again a what we can call that to be a pinacol. Pinacol, it undergo contraction of the ring in presence of perchloric acid. The reason is that what would be the reason for that? There will be, for example, let there be deprotonation over here. H+. What happens is that here there will be CH3. So there will be OH, this positive charge here, CH3. There will be breakage. There will be migration of this bond towards this bond. that leads to the formation of long numbered ring. Okay, and this is actually what is happening over here, and you can better explain the phenomena. Okay, so there's a new bond formed between this carbonatom and this carbonatom. You can see that this is migrated towards here and it forms 5-membered ring, and it forms a system like this. Again, the similar example is applicable over here. We can check here also a pinacol is formed, and there's a carbocation. This bond shift towards this. If there will be a carbocation here, what happens? This bond migrates towards this carbon, and it forms a 3-membered ring. For getting more examples and if you're getting more information, you can use this link. There is a link called chemistry.chem.liberate. And actually, if you look into this sheet, you may get a good examples of pinacol rearrangements. Now, these are some of the homeworks. Some of them we had discussed already before. See, these are the compounds. We have to predict the compounds of pinacol-pinacolone rearrangement. These are the pinacols that we are using. Okay, you try the 1, 2, 3, 4, 5, 6. There are 6 compounds are here, and you have to go through these 6 examples and give the products. So good typical example of pinacol-pinacolone rearrangement here. There are 3 possible products here. We are supposed to explain the presence of all these compounds. We have to explain the mechanism of explaining this product formation. We have to explain the product formation of this compound. It is by simple elimination. I can say that it is by simple elimination. What happens is that this double bond and double bond forms. The first compound can be explained. Second compound can be explained if this OH is going off, the bond shift towards this place and this bond. And this OH is removed first, then what happens is that this will migrate to this place and this bond. You may try to figure out the detailed mechanism of this these things and submit. Okay, and the 3 examples is cited here. Okay, please try to explain the formation of the co-products. So pinacol-pinacolone rearrangement is actually a typical reaction, and it's a very important reaction. Lot of studies have been conducted on that, and therefore I strongly suggest you guys to go through these type of reactions and see what is happening here. We can use any organic chemistry textbooks. They give wonderful account of pinacol-pinacolone rearrangement. Thank you very much.